After you've gotten through the PowerPoints in 6.1, let's take a look at several example problems from homework. The first one we'll take a look at is number 5. It says, find the critical value z sub c necessary to form a confidence interval at the level of confidence shown below. And our level of confidence is 0.95. 0.95. So if we draw a normal distribution, the mean is in the middle. We want a confidence interval of 0.95, which means when we go to the left and to the right in equal amount, there's a 95% chance that that interval that we formed contains our mean. So we need to find out what z value here, which the opposite of that z value will be here, what z value is a boundary that closes in the middle 95% of the data. So we're going to use our normal distribution table to do that, but in order to do that, remember our normal distribution table takes care of the area to the left of z. So let's find out about the tails. If 95% of the data is in the middle, then the tails, the left and the right tail, have everything that's left. So if we take 100% and subtract 0.95, 5% or 0.05 of the data is in the two tails. Those tails are the same size, so if we take half of that, that tells us how much is in each tail. So this tail has 0.025 in it. This tail has 0.025 in it. So one way the book may explain is by saying if we have 0.025 in this tail, then we can find the area to the left of that critical value z. But an easier way to do this is if we know that the area in this section is 0.025, notice that's the area to the left of this z value. So let's take our table and look up that area and find out what z corresponds to it. So let's go over to our table and find out what z value corresponds to a left tail of 0.025. So remember, the area is the numbers in the middle. The z's are the outside numbers. So if we go to 0.025, here is 0.025. That corresponds to a z value of negative 1.96. So this z is negative 1.96. Since this is symmetric about the mean, then this z value is positive 1.96. So they're going to say that the critical value for this confidence interval is 1.96. So let's put that in and see if they take our answer. So if we go over here and put in 1.96, not 1.6, 1.96. We got it correct. So that's finding our critical value. Right, next, let's move on to this one. Find the margin of error for the given values of C, sigma, and n. So let's see if it'll let us copy these over. All right, so our confidence is at a 90% confidence level. So let's just sketch our normal distribution. So our mean is in the middle. Our confidence interval is 90%, 0.9. So that means we have an area of 0.9 inside here, which means whatever is left is in the tails. So our tails have an area of 0.10. Each tail has half of that. So if we divide that by 2, we have an area of 0.05 in each tail. So knowing that the area of the tail is 0.05, that allows us to find the z-value, the critical value. Once we know the critical value, the margin of error is the critical value times the standard deviation of the population divided by the square root of the sample size. Now, you may recall that that calculation gives you the standard deviation for the sampling distribution of sample means. So this is essentially the standard deviation of our sampling distribution. If we know what the standard deviation is, z is a count of how many standard deviations we have. So, for example, if z were 2 and our standard deviation was 1.4, our error would be 2.8. If we move 2 standard deviations, we've moved a distance of 2.8. So that's what E is. How far from the mean are our boundaries? So we need to find that z value. So we've determined that the area of the left tail and the right tail is 0.05, but this one is the one that helps us the most, because when we go to our table, remember it's a cumulative table. It gives us the z value when we know the area to the left, or if we know the z, it gives us the area to the left. So let's look up an area of 0.05. So if we go to our table and find an area 0.05, it's somewhere in between these two, negative 1.65 or negative 1.64. That's the critical value on this side. So our critical value is 1.65 or 1.64. So our margin of error is that critical value times our population standard deviation divided by the square root of our sample size. So if we pull out our calculator, 1.65 times 3.5 divided by the square root of 36, and that gives us 0.9625. So if we knew what our mean was, then our margin of error to the right of the mean or to the left of mean would be that distance. So let's put that in and see if that's what they're looking for. They say it around to 3 decimal places. We'll go with 0.963. They may have also wanted us to round our critical value to 3 decimal places, which would have been roughly between the two z values that we saw in our table. Well, let's try this. All right, that's what they wanted. Okay, next, let's take a look at this one. Construct the confidence interval for the population mean mu. Our confidence interval, or our confidence level is 0.95, so 95% confident. Our sample that we have taken has a mean of 8.4. Our population has a mean of 0.9, and our sample size is 56. So let's see if we can copy this over. So if we draw our distribution of a normal distribution, the mean is in the middle. We have a 95% confidence level, so 0.95 is the area in the middle. If we remember on our last problem, 2 problems ago, our confidence level was 0.95. So the critical value is going to be the same. We have a critical value of 1.96. So our z value, 1.96 this way, negative 1.96 this way. So if we want our confidence interval, the right side comes from taking the mean plus the margin of error. The left side comes from taking the mean minus the margin of error. We know how many standard deviations it is, but we want to translate that into actual data values. If we know what the mean is, how far in terms of our data, not how many standard deviations, but how far from the mean, or how far below the mean does it take to have that confidence level. Times our standard deviation over the square root of n. So 1.96 times 0.9 divided by the square root of 56. So let's get our margin of error. So if we go, how many decimal places do they want here? They want 2 decimal places. So 0.24, 0.24 is our margin of error. So our upper boundary will be our mean plus the margin of error. Our lower boundary will be our mean minus our margin of error. So the margin of error, again, that's how far are we going to the right, how far are we going to the left from the mean. Z is a count of how many standard deviations that is, but 0.24, that's how many units are we traveling, not how many standard deviations. So if we do 8.4 minus 0.24, we get 8.16. If we do 8.4 plus 0.24, we get 8.64. So that's our error interval for the 95% confidence level. So let's put that in. 8.16 to 8.64. And that's right. So the next one, they give us the confidence interval and they want us to find the margin of error. So if our confidence interval goes from 1.55 to 1.93, just roughly sketch this. This is not a z-value, this is an x-value. Remember, we center this about the mean. So the mean is halfway between those. So the distance from the mean to that side is the margin of error. From the mean to that side is the margin of error. So the distance between the lower interval and the upper interval is twice the margin of error. So if we subtract 1.93 minus 1.55, 0.38, that's twice the margin of error. So if we want the margin of error, divide both sides by 2. So our margin of error is 0.19. And that's what they're looking for there. Alright, so let's do this one next. Find the minimum sample size to estimate the mean of the population for the given values. So let's copy our given values. So if we sketch a distribution, in the middle we have the mean. Our margin of error is 2. They give us a standard deviation, and they give us the confidence level. So remember, we've done this confidence level several times, of 0.95. That gives us a critical value. Go back. Confidence level of 0.95, our critical value 1.96. So remember the way we calculated the margin of error. It was our critical value times the standard deviation over the square root of the sample size. We know the margin of error. We know the critical value. We know the standard deviation. What we don't know is n, the sample size. So we just need to solve this equation. Let's begin by combining these. So if we do 1.96 times 9.3, we get 18.228. On top, the square root of n on bottom. To get rid of the denominator, to make our fraction go away, multiply both sides by the square root of n, so those cancel. So on the left, we just have 18.228. On the right side, we have 2 square roots of n. If we want to get the square root of n by itself, divide both sides by 2. So the square root of n is 9.114. So that's the square root of n. If we want to know what n is, to get rid of a square root, we square both sides. So n is 9.114 squared, 83.06, which rounded to the nearest integer. We need a sample size. We have to be careful. It says find the minimum sample size. When we do our calculation, we get a value that is really over 83. So if we round down to 83, 83 is smaller than the necessary sample size. Notice they also give us a clue here. We want to round up to the nearest whole number. Our sample size has to be an integer value, a whole number. So to make sure that we have at least this many, then we're going to use the value 84 for the size of the sample that we need. So we need a sample size 84. All right, let's take a look at another one. Let's look at this one. You're given the sample mean and the population standard deviation. Use this information to construct the 90% and the 95% confidence intervals for the population mean. A random sample of 50 home theater systems, so let's write that down, N is 50, that's the size of the sample that we're collecting, has a mean price of $139. So our sample mean is $139. Assume the population has a standard deviation of $18.90. So for our population, the standard deviation, $18.90. So we want to use this to construct our 90% confidence interval. So let's just sketch. We should have a normal distribution by the time we have a sample of that size. So our sample mean, which is also an estimate of our population mean, is our point estimate. It's 139. We want to go far enough to the right and that same distance to the left so that we have 90% of our data on the inside. So we need to find the critical value that cuts off between what's in the 90 percentile and what's not. So we've looked that up several times. Let's just go back and see if we had 90% on any of these. So for confidence of 90%, our critical value is 1.65. Oops. So 1.65, that's our z value. So in order to get our interval from the mean, our population mean, it's going to be less than the sample mean plus the amount of error, and it's going to be bigger than the sample mean minus the amount of error. So we need to find our amount of error. So remember, that's our critical value times the standard deviation divided by the square root. So 1.65 times 18.90 divided by the square root of 50. So our error, not sigma, our error should be, let's see what this comes out to. About 4.41. So if we take our mean plus 4.41 and take our mean minus 4.41, then we can be 90% confident that the population mean is inside that interval. So 139 plus 4.41, 143.41. 139 minus 4.41, what's that, 134.59. So that's the error interval we're looking for, 134.59 to 143.41. So that's the 90% confidence interval. That's the interval with which we're 90% confident that the true population mean is in that interval. Now, the second part of this asks for us to find the 95 percentile confidence interval. So 139, our mean, is still in the middle, and we want to go far enough to the right, far enough to the left, so that 95% of our data is in that interval. So I believe we have done a 95%. Yep. The reason I say I wonder is been 3 or 4 days since I've done the rest of these problems. I ran out of time. I'm having to pick back up. So yes, with 95% confidence, our critical value is 1.96. So our z-value here is 1.96. Our z-value here is negative 1.96. So if we want to find our error, it's our critical value times standard deviation divided by the square root of our sample size. It's a 1.96 times 18.9 divided by the square root of 50. So this will be our error for the 95% confidence. So that comes out to be 5.24. So our confidence interval will go on the top side, our mean plus 5.24. On the bottom side, it's 5.24 below the mean. And that will give us our confidence interval. On the top side, that's 144.24. On the bottom side, that's 133.76. Notice if we compare those intervals, the second interval is a little bit wider, which, if we think about it, to be more confident that we're inside an interval, it would take a wider interval. If we have a really narrow interval, if our interval was just, let's say, 1 standard or a half a standard deviation wide, half a standard deviation for the mean, then it's still possible that the population mean would be inside that interval, but when we collected our sample, it might not have been a representative sample, so the likelihood that our population mean is in there is not as good as it would be if we have a really wide interval. If we went 4 standard deviations to both sides, then that would have almost all of the possible sampling distributions inside that interval. So we can almost guarantee our population be inside that interval. Is that our population mean is inside there. We don't want to get too wide, because the wider our interval is, the less that tells us about what the population mean actually is. It's narrowed down a lot less, but we want to be wide enough that we're pretty confident. So the top one was a 90%, the bottom was a 95%, which was a little bit wider, but not a ton wider.